in this video, we're going to discuss the moment area method for computing displacements in beams. So we will start by considering a beam that has an arbitrary distributed load. And then let's define 2 points on the beam. We'll call that A and B, the distributed load. And so now let's look at, so if we think about the moment function divided by EI, right? We'll sort of just draw that. Right, so this would be the M over EI diagram. And it's also labeled the 2 points A and B. And now let's look at an infinitesimal length of the beam. And we'll call that dx. Now, in a previous video, we established the relationship between the moment, the flexural rigidity, and the change in slope, right? So we established this relationship when we formulated the differential equation for beam bending. So looking at the M over EI diagram and the equation for the change in slope, we see that looking at the M over EI diagram, we see that the change in slope on either side of dx is equal to the area under the M over EI diagram. All right, so basically what we're saying is this area is the change in slope. We'll call that d theta. So what that means is if we integrate the M over EI diagram between points A and B, that will actually give us the change in slope between those 2 points. And we'll define that as theta BA. That would be the integral of the M over EI diagram between points A and B. So this is basically the first theorem associated with the moment area method. It basically says that the change in slope between any 2 points on the deflected shape is equal to the area of the M over EI diagram between those 2 points. Now, if we think about, let's think a little bit more about what that angle represents. So let's draw the deflected shape of the beam. So what that angle theta B represents, it's the angle of the tangent at B measured with respect to the tangent at A. So if we again label point A and point B, we can draw a tangent at A. We'll call that tangent at A. And then we will also draw a tangent at B, right? that theta BA represents this angle between the two tangents. And we also see that that angle is measured counterclockwise from the tangent at A, from the tangent A to the tangent B, if the M over EI diagram is positive, right? So in this case, we have a beam that's bending such that it's concave in the positive local y direction. So that means we have a positive moment. So the M over EI diagram is positive. So again, the angle is measured counterclockwise from the tangent A to tangent B. On the other hand, if the area is negative, if that area under the M over EI diagram is negative, or if it's below the x-axis, then theta BA would be measured clockwise from tangent A to tangent B. So now let's focus on the second moment area theorem, which is based on the relative deviation of the tangents of the deflected shape. So let's look at the deflected shape of the beam again. We have our 2 points A and B. And we have our tangent from A. We have our tangent from B. We're interested in the relative vertical deviation between those two tangents. And that we call TAB. Now, if we take another look at our infinitesimal strip of length dx, we can also draw tangents from the two ends of that strip. And we'll call this distance dt. So dt in this case is the vertical deviation of the tangents on each side of dx. And this deviation is measured along the vertical line passing through A. All right, so it's measured along this vertical line. Now, given that the slope of the deflected beam and the deflection itself are assumed to be very small, we can approximate the length of each of the tangent lines by x, right? So when we say x, we're referring to this distance, right? So we're going to approximate the length of these two tangents by the dimension x, and then the arc that we'll call ds prime will approximate that by dt. So if we use the formula for an arc, and that formula says that the arc length is equal to theta times r, where theta is the angle, is the change in the angle, and r is the radius, then that means we can also write that dt is equal to x d theta, right? Where d theta is the change in angle between the tangents on both sides of dx. Now, recall that we established a relationship that says d theta is equal to m over ei dx. Then that means that the vertical deviation of tangent A with respect to tangent B can be found by integration, right? So if we take this relationship and we apply it to find the vertical deviation of tangent A with respect to tangent B, we get this relationship. Right, where this part of the equation is the area under the M over EI diagram. Okay, we also know from statics that the centroid times this integral is also equal to the integral of x times dA. And since the m over EI dx integral represents the area of the m over EI diagram, that means that we can write the deviation as this expression, where the x bar is the distance from the centroid of the area under the M over EI diagram to the point A. Right, and so this establishes the second theorem of the moment area method, which says that the vertical deviation of the tangent at a point A and the deflected shape with respect to the tangent extended from another point B is equal to the moment of the area under the M over EI diagram between the 2 points. Now, keep in mind that this moment is computed about point A, and TAB is the deviation that is to be determined, right? So again, this is the distance from centroid of M over EI diagram to point A. So a couple of things to note. Again, if you have a positive M over EI area between A and B, then the tangent at point A is going to be above the tangent to the curve extended from point B. So let's try to visualize that. So if we draw again the deflected shape, we have point A, we have point B. For this deflected shape, we know that M over EI diagram is going to be positive. And if we extend the tangent from A and we extend the tangent from B, right? We see that the tangent at point A is above the tangent to the curve extended from point B. And on the other hand, if you have a negative M over EI diagram between A and B, then the tangent to point A will be below the tangent to the curve extended from point B. Another thing to keep in mind is that the deviation from A to B is not the same as the deviation from B to A. And this is because the moment is taken about point A to find TAB, and it's taken about point B to find TBA. Another important thing to keep in mind about the moment area method is that it only gives the angle or deviation between 2 points on the deflected shape. It does not give the direct solution for the slope or displacement at a point. So that's something that needs to be kept in mind. In the next video, we're going to implement a couple examples where we use the moment area method to compute beam deflections and slopes.